An air bubble rises from the bottom of a well, where the temperature is 20 degrees Celsius, to the surface, where the temperature is 30 degrees Celsius. Find the percent increase in the volume of the bubble if the depth of the well is 30 meters. Atmospheric pressure is 101,600 pascals. So let's draw our schematic diagram. Say this is our well, and the problem mentions that there's an air bubble, and it's at the bottom of the well. And say the bottom of our well is, this is our point 1 here. We are told that at point 1, the temperature is 20 degrees Celsius. Now the air bubble rises to the surface of the well. So say this is our surface here, this is our bubble, this is our point 2. And the temperature given is 30 degrees Celsius. Now we are to find the percent increase, or if we find the percent increase in terms of volume of the bubble if the depth of the well is 30 meters. So the depth should be from point 2 to point 1, and denote this by h. This is 30 meters. So that's the depth. It's too deep. And we're also provided that the atmospheric pressure is 101,600 pascals. So that's atmospheric pressure is equal to 101,600 pascals. Take note that atmospheric pressure is applying pressure to the surface of, or on the surface of the well, because the surface of the well is always, or most of the times, surface, this is open to the atmosphere. So I'm just indicate that this is open to the atmosphere. So this means that at point 2, the pressure there is just equal to the atmospheric pressure. So I think we have everything needed. I mean, in the given of the problems already in the schematic diagram. So the percent increase in terms of volume, that's what we are asked to find. This is just equal to the change of volume. So that's the percent change. This should be over the initial volume. So that's V1. And delta V is just equal to V2 minus V1 all over V1. So basically, if we know the values for V2 and V1, then we can already solve the problem. But we're only provided with temperatures and a pressure. So what we can do here is, if you can recall the equation of state for an ideal gas, this should be PV is equal to MRT. We can treat this problem as an ideal gas problem, and air is in our ideal gas. And this ideal gas equation, we can rearrange this so we can have this in terms of volume, because that's what we need here. So this should be MRT all over P. And take note, if we're gonna input that here, MR will just cancel out. So I'm just gonna write that down. So this will become, this is gonna be our working equation. So this is gonna become T2 over P2. And this is minus T1 over P1. And this is also, V1 is T1 all over P1. So basically, if you know the temperatures and pressures, then you can already solve for the problem. We've got T1, T2, and P2. So we're just left for, we're just left with T1 to solve. At point 1, you can just recall the basic pressure. That's should be P is equal to the specific weight of whatever fluid times the height. And if we apply that here, this is just variations of pressure in the fluids. So just gonna write that down, that the pressure here is basically, that's P1. That's basically what the pressure of whatever fluids inside the well, and that will be the specific weight of that fluid multiplied by the height, which is, we've got 30, and we add the pressure on this surface here. So that's P2. And at this point, we're going to assume that the fluid in the well is just water. That's mostly the case. So a specific weight of water, I'm going to use the pascals. That's not, because we need to have the P2s in terms of pascals. So I want to use 9,810 newtons per cubic meter. So that this will be multiplied by the height, which is 30 meters. And the pressure too is 101. So that's 101,600 pascals. If we're going to do the unit analysis, this meter here will just cancel out this meter here, 1 meter. So that's Newton per meter squared. And Newton per meter squared, this is just equal to pascals. So we've got our answer for P1 in terms of pascals. So if we get our calculator, this should be equal to 9810 multiplied by 30, and we'll add 101,600 pascals. So this is our pressure at point 1. 3, what was that again? 395, 900, 395, 900 pascals. So you can already solve for our percent increase here. Just gonna write this down here. Percent increase, this is equal to, our temperature 2 is equal to 30 degrees Celsius. Take note, if you're going to be using ideal gas equations, make sure that temperatures and pressures are in absolute, because that's what you need. And if you've noticed, I've used in my given a small letter t and and I've got the capital P here. This is just for me, just a way for me to remind myself that it's the temperature I'm writing down is just still in it's still not in absolute. So what I'm gonna do here is we'll just convert that right straight to in our problem. I mean in our solution. So T2 is gonna be 30 degrees. We'll add 273 to make this in kelvins, and that's the absolute temperature. And this will be over the pressure at point 2, which is equal to just the atmospheric pressure, which is 600 pascals minus 20 degrees Celsius plus 273 all over the pressure at point 1, which is equal to the one that we've solved, 395,900 pascals. And this is all over same T1, which is 20 plus 273 all over 395,900. So let's just use our calculator first. We're gonna need this one. It's 30 plus 273 all over 101,600 minus I need another fraction here, so that's 20 plus 273 all over 395,900, and just need another fraction, 20 plus 273 all over 395,900, and this is equal to 3 is equal to what was that again? 3.03. So that's equal to 3.03. Oh, it's still not 10%. 3.03. Of course, we'll have to multiply this answer by 100% because we're asked, oops, 3 multiplied by 100%. This is 303%. So basically, this is our final answer. And what this means is, say for example, this is our well, and this is our volume 1. If it will be increased by 303%. So let's just make it 3 times larger. The bubble should look something like this. An ideal gas has an initial pressure of 50 psig and a temperature of 90 degrees Fahrenheit. It is heated in a closed container to 150 degrees Fahrenheit. What is the final pressure? So this problem, we can just use the combined gas law. Let's put our given first. We have the initial pressure. So our initial pressure, this is P1 is equal to 50 psig. And we have a temperature of, so this is our T1 is equal to 90 degrees Fahrenheit. Heated in a closed container to 150 degrees Fahrenheit. So our temperature 2 is equal to 150 degrees Fahrenheit. We are asked what is the final pressure. Now, we can use the combined gas law here, which states that PV, this is basically PVT is constant. So this means that P1 V1 T over T1 is equal to P2 V2 over T2. Now, take note that the container is closed, and so there's no mass coming in, or the volume, basically because the container is closed, the volume of the ideal gas is this is constant. It can't expand. It will just take up the space inside the closed container. So basically that means that V1 is equal to V2. That's what this means with a closed container, and it's a gas. Since this is a gas, then we can safely assume that V1 is equal to V2. So basically, we're left with P2. I'm just going to write that down here. P2 over T2 is equal to P1 over T1. So if we transfer this here, we can rearrange this equation to have it in terms of P2. I'm going to write that down here. So this is going to be P2 is equal to P1 multiplied by T2 over T1. So this is going to be our working equation, and basically we've got everything that we need. But what we need to do, take note, if you're going to be working with ideal gas equation, make sure that you'll be working with absolute temperatures and pressures. In our problem, we are provided with 50 psig is our P1, our first pressure. So if you recall the absolute pressure, this is just equal to the atmospheric pressure plus the gauge pressure. You're already provided with this one. So you should, if you're not provided with the atmospheric pressure, you should memorize, or you should be familiarized with the values of the atmospheric pressure. And in this case, since we have atmospheric or the gauge pressure in psi, we can just use 14.7 psi as a standard atmospheric pressure, plus the 90 or 50 psig. But we're gonna psig here, so let's just input that straight here. So that's 14.7 plus 50. This is psig. It's not gonna PSIG, or not PSIG, this is already an absolute. we'll multiply that with temperature, and take note the temperature is the second temperature, or the temperature at point 2 is 150 degrees Fahrenheit. Let's just convert that directly to absolute. So that's 150 plus 460 all over 90 plus 460. This is to make this in absolute. So again, this is going to be in terms of PSI, because the units in our numerator and denominator will just cancel out. So where's our calculator? So if we have 14.7 plus 50, and we multiply this by, multiply that by our fraction, which is 150 plus 460 over 90 plus 460, and we have our answer is 71. So this is 71.76. So this is going to be 71.76 psi, and this is in terms of absolute. So this is our pressure 2. Or if you're asked to have it in gauge pressure, then you can just minus 14.7 again to make this in gauge pressure. So that's 57.06 psij. This is our answer. Air pressure in a 5,000 cubic centimeters compressed air tank drops from 1,000 kilopascals to 200 kilopascals, while the temperature remains unchanged at 25 degrees Celsius. What percentage has the mass of air in the tank been reduced to? So if we're gonna reduce, or if we're gonna draw our schematic diagram, say this is our compressed air tank at state 1. We say this is our gauge pressure, and this is pressure 1, or our pressure at state 1 is 1,000 kilopascal. Now the temperature here remains unchanged. So T1 is equal to 25 degrees Celsius, and this is equal to our T2 here. So we have T2 is equal to 25 degrees Celsius. We're just going to write that down. So this is going to be our state 2. This is the same tank, by the way. We have a volume of 5,000 cubic centimeters. The volume here is still just 5,000 cubic centimeters. Nothing has changed. The only thing that changed is the pressure. It dropped from 1,000 kilopascals to 200 kilopascals. So we are asked what is the percent change in terms of the mass. So our percent change in terms of mass, we're just gonna percent change in terms of mass. So this is just equal to the change of the mass. This will denote that delta M over the initial mass. So basically this is just M2 minus M1 all over M1. So the problem, it's already said that the mass has been reduced to. So basically from here, I can already say that M2 is lesser. M2 is lesser than M1, but M2 is lesser than M1. That's, I already know that. So but as of now, from our, we can actually solve this in 2 ways. First, since we're provided with the values, we can solve for the mass at state 1, and then by using the values, they're like the properties of the air it's given, and then we can solve for M2 in state 2. Or we can just use, you can just solve this directly using the variables. Let me just write that down so you know what I'm talking about. So if you can recall, the ideal gas equation is PV is equal to mRT, right? We'll be rearranging this in terms of the mass. So this will become PV over RT. Now, I already have an equation for the mass. If I'm gonna plug that here, what's gonna happen is the R will just cancel out. It's gonna be the same. It's constant. I'm gonna assume that it's gonna be constant, and the volume will change as well, because nothing has changed. This is just slightly bigger. Let me erase this one to make this a little bit similar. They're just the same. Nothing has changed, and this will cancel out. And we're also provided with the information that the temperature remains unchanged. So basically, temperature remains unchanged. So what we're left with is basically the mass is proportional to, direct proportional, or is equal to the pressure in this scenario. So all we need to do is, since we already have the pressures in our problem, it's just directly input our pressure, and the unit will just cancel out. So basically 200, so that's our P2. Just write that down first. So this is going to be P2 minus P1 all over P1, and that's going to be 200 minus 1,000, or minus 1,000 all over 1,000. And this means that 200 minus 1000, this is going to be negative 800 all over 1000. So basically this will cancel out. It's 8 over 10, so we have negative 0.8. Multiply this by 100% because we are dealing with the percent change here. So we'll have basically 80 percent. 1, 2, that's 80, and this negative indicates that the mass has been reduced to. How much work is needed to compress air in an insulated cylinder from 0.40 cubic meters to 0.02 cubic meters when the initial temperature is 25 degrees Celsius and the initial pressure is 102.520 kilopascals? So let's draw our schematic diagram. Say this is our cylinder, and the problem says that this is insulated. So this is insulated here. And when the initial temperature, we're provided at state 1 with 25 degrees Celsius. We're also provided with initial pressure. So P1 is equal to 102.520 kilopascals. I think we've got the volume. So volume 1 is equal to 0.40 cubic meters, and this is compressed. This is compressed. I'll say this is my piston here, and you've got your what's compressed air here inside. The volume here is V1, and that's compressed to here. This is my piston, and this is already my air compressed to down to V2 is equal to 0.02 cubic meters. So this is the process, and okay, this is still insulated. So what we're going to do here is first we are asked how much work is needed. We're not provided with the process, so we need to identify what type of thermodynamic process this is, so that we can proceed with our solution. So take note that the problem mentions the cylinder is insulated. So basically, if everything is insulated, we can assume that there's no heat that's coming in the process. So Q is equal to 0. Now we're going to assume that this is a reversible process as well, because if there's no heat that's coming in to our system, we can say that the process is adiabatic, and we assume that this is reversible process, because we can just assume this is an ideal process. So this is going to be a reversible adiabatic, and reversible adiabatic is just isentropic process. And if isentropic process, if you can recall, PVK is C. This is the relationship with isentropic process. But the work here, not going to derive it for you, but basically, if you know the different thermodynamic processes, because thermodynamic process, which we will have another video for that, then all you need to do is just identify what process it is, what the problem is talking about, and use the formulas that's pertaining to that process. So within an isentropic process, work is basically just the change of PV, this value here, over 1 minus K. So basically what this means is this is P2 V2 minus P1 V1 all over 1 minus K. So this is the formula for work in an isentropic process. I'm not going to derive here because we've got another video for that as well. But for now, we're provided with our pressure 1 and our volume 1. And we are also provided with our volume 2. We're not provided with pressure 2. So we can just use this isentropic relationship to solve for our pressure 2. And this means that PVK, so that's P1 V1 raised to the power of K is equal to P2 V2 raised to the power of K, because that's constant. PV raised to the power of K is constant. So if we're going to be solving for P, let's just rearrange this one. This will become P1 V1 all over V2 over K. We have value for P1, we have value for V1, V2. So basically we can solve for the end, this RP2. K, if you're not given, this is also something that you should be familiar with. The value of K, which is the heat capacity ratio of air, is just 1.4. It's the standard. K is equal to 1.4. We can just assume it to be a 1.4 value if it's not given. Of course, in reality, this varies with the temperature, but for now, let's use 1.4 K as the standard value for the K of air. So this is going to be P1 is 102.520 kilopascals. I'm going to assume that this is already in absolute. If it's not given in the problem that the pressure is in absolute, you can assume it to be in absolute. This is 102.520 kilopascals. and this should already be an absolute, and all over V1. So our V1 is 0.40. This is cubic meters, and this is 0.02 cubic meters. That will just cancel out the unit. Raise to the power of 1.4. So our P2 is just equal to P2. So that's 102.520 multiplied by a fraction. So this is 0.4 all over 0.02 raised to the power of 1.4. So this is our pressure 2. So this is 6,000. What was that again? 6795. Let's make this 6796. 6796 kilopascals. It's a very, very huge gap. This is a very big pressure from. Take note, this is from 0.40 to 0.02. But anyway, that's our problem. So let's just write that down here. So our pressure 2 is equal to 6. I'm gonna move this one first. Let me just move this one first. This one here. Okay, so we have 6, 7. So back to our problem, we have 6,796 kilopascals multiplied by V2, which is V2 0.02 minus our P1 is 102.520. Oops, it's 520 multiplied by 0.40, and the units here is kilopascals and kilopascal. Kilopascal cubic meter. Kilopascal is just equal to kilopascal is just equal to kilonewton per cubic or per meter squared, and our volume is cubic meters. So this will cancel out. Yes, you know, right? This will cancel out, and one unit by unit analysis, this will cancel out here as well. And we're left with 1 meter, and value is 1 minus the denominator is 1 minus 1.4, and kilonewton meter is just equal to kilojoule. So basically we have our answer in terms of kilojoule, and that should be equal to so let me just do a fraction first. 6,796 multiplied by 0.02 minus 102.520 multiplied by 0.40 all over 1 minus 1.4, and this should be our answer, and this is negative 237, negative 237.28. This is kilojoule, and this means that negative means that work is done onto the system. This is our system here, and work is done into the system. Needs work of 237.28 kilojoule. That's our answer. An engine is operated between temperature limits of 1550 degrees Celsius and 320 degrees Celsius. Engine is applied with 15,100 kilojoule per kilowatt hour, and we are asked the Carnot cycle efficiency in percent. This is just actually a straightforward problem that we're gonna be deriving the formula here. This will come in handy if you have memorized the formula. But if you can recall the Carnot cycle TS diagram, or let's say this is the TS diagram here. Say this is my point 1, and this is my point 2 here. It goes from this one, and it goes here. This is point 3. It goes here. This is point 4. So this is basically the TS diagram of the Carnot cycle, and QA is added here, and heat is released here from system 1 to 2. It's over. So this means that from 1 to 2, this is an isentropic expansion, and the system is doing work. From state 2 to 3, it's a constant temperature. Heat is released in a constant temperature process, and from state 3 to state 4, it's isentropic compression, and from state 4 to state 1, it's an isothermal heat addition. So basically, this is our schematic diagram for Carnot cycle, and QA heat added is just equal to the temperature T4 or T1, or I'm going to indicate this as our high temperature. Because this, you only have two temperature here, and this one, T4 and T1 is equal, and T3 and T2 is equal. And this is QA is equal to TH, or the higher temperature, multiplied by the change of entropy. So this is the change here of entropy. This is delta S. And QR is just equal to the lower temperature multiplied by delta S. Now work, we can do an energy balance in this in our diagram, and energy in, energy out, and what's coming in is just the QA, and what's going out is work plus QR. So basically work is equal to QA plus, or minus rather, QA is equal, or QA minus QR. So this is already our work once here. And in terms of efficiency, efficiency, this is just the output over whatever is being the input. This is the general formula for efficiency. In our case, the output is the work net, or so the work, which is equal to, so this is work, that's the output. And our input is QA, it's heat added. This is our work output. And work is just equal to QA minus QR. And this is all over QA. And if we further simplify this one, this is going to become 1 minus QR over QA. So from here, we can use this relationship here. Oops, so use this relationship here. We will have this 1 minus QR is TL multiplied by delta S over QA, which is TH, over multiplied by delta S. So basically, this is going to be our final equation for efficiency. This will cancel out. This will cancel out. So basically, if you know this formula, it's very easy for you to answer this problem. Basically, you just need to know the two temperatures. So this is, you'll be able to answer the Carnot cycle efficiency, and Carnot cycle efficiency is the highest efficiency of in terms of thermodynamic processes or cycles. So our efficiency is going to become 1 minus TL, which is the lower temperature, 320 over 1,550. And take note that if you're going to be using this formula, make sure that your temperatures are in absolute. So this is 320 plus 273 to make this absolute, plus 273, and we basically have our answer. And we have our calculator. We just have to input 1 minus the fraction 320 plus 273 all over 1550 plus 273. And of course, we'll have to multiply this by 100%. So basically, this is 67.47%. 67.47%, and this is the efficiency of our engine with the temperature limits of 1550 degrees Celsius and 320 degrees Celsius. And if you want to increase the efficiency of your the Carnot cycle efficiency of your engine, basically you just need to keep this low. You need to keep this low, and you need to keep this high. And this will increase this value here.